In question 1, we've got y being 3x to the 4 minus 8x cubed minus 3, and we are asked to find the first and the second derivatives. So for the first derivative, we get the power down and we deduct 1 from the power. So 3x to the 4 will give me 12x cubed minus 24x squared. Now for the second derivative, we will take the first derivative and differentiate once more. We get 36x squared minus 48x. We are then asked to verify that C has a stationary point when x is 2. We know that stationary points mean that the dy dx at this particular point must be 0. We have been asked to verify, so I'm just going to take the x is 2 and substitute it into dy dx. So I will evaluate dy dx at x is equal to 2. So this leads to 12 times 2 cubed minus 24 times 2 squared, which gives an answer of 0. And therefore we conclude that C has a stationary point at x is 2. In part C, we need to determine the nature of the stationary point, giving a reason for our answer. Well, since we have found the 2y by dx squared, I will use the second derivative test to establish the nature of the turning point. So the 2y by dx squared evaluated at x is 2 is equal to 36 times 2 squared minus 48 times 2, which gives an answer of 48. This is greater than 0, and therefore we conclude that we're looking at a minimum point. Remember that with the second derivative test, if you get a positive result, you conclude that it's a minimum. If you get a negative result, you conclude that it's a maximum. And if you get an answer of 0, then the test is inconclusive. You also need to show explicitly the comparison with 0 in order to justify the conclusion on the nature of the stationary point. In question 2, we've got the shape ABCDOA, and it's a sector COD, this part here, and a circle centered at O with the sector AOB shaded here. We have that the arc length CD is 3 centimeters as shown on the figure. Angle COD 0.4 radians and AOD is a straight line of length 12 centimeters. And we need to find the length of OD. OD is the distance here. So let's start by reminding ourselves that the length of the arc is given by r theta when theta is in radians. We know that the length of the arc is 3 centimeters. We are looking for the radius r and the theta is 0.4, which means that we can find r by doing 3 over 0.4, and this gives an answer for r of 7.5 centimeters. That's the length of OD here. It's the radius for the sector ODC. In part B, we need to find the area of the shaded sector AOB. So let's start by reminding ourselves that the area of a sector when theta is in radians is given by a half r squared theta. We know that the angle AOC here is pi minus 0.4. We have found r to be 7.5, and therefore the distance AO is simply 12 minus 7.5, which works out to be 4.5. That's the radius for the sector which is shaded here, the sector ABO, and therefore the area will simply be given by a half times 4.5 squared times pi minus 0.4. Plug everything on the calculator, we get an answer of 27.8 squared centimeters. In question 3, we've got the circle C with the equation x squared plus y squared minus 4x plus 10y is k, where k is a constant, and we need to determine the coordinates of the center of C. Well, one way we can do this is put the circle equation in a standard form, bearing in mind that the circle centered at alpha beta with a radius of r has equation x minus alpha squared plus y minus beta squared is r squared. So I will be completing the square here. We've got x squared plus y squared minus 4x plus 10y is k. Let me start by writing this as x squared minus 4x plus y squared plus 10y is equal to k. And we complete the square. We have x minus 2 all squared minus 2 squared plus y plus 5 all squared minus 5 squared is k. leading to x minus 2 squared plus y plus 5 squared minus 29 is k, and therefore we have that x minus 2 squared plus y plus 5 all squared is equal to k plus 29. If I compare my equation here with the standard equation, we see that the center must be the point with coordinates 2, -5, and that's the answer to part A. And then in part B, we need to state the range of possible values for k. Well, we know that k plus 29 must be the r squared. So if I state that r squared is k plus 29, then we know that the radius squared can never be 0 or negative. It has to be strictly positive. So this leads to k being greater than minus 29. In question 4, we are told that a is a positive constant such that the integral of t plus 1 over t dt from a up to 2a is ln 7, and we need to show that a is ln k, where k is a constant to be found. Well, starting from the given integral, the first thing to do is express this on a term by term basis. So it's t over t plus 1 over t dt, which of course simplifies into the integral from a up to 2a of 1 plus 1 over t dt, which gives t plus ln t. The integral of 1 over t is ln t from a up to 2a. I will now substitute the upper limit to get 2a plus ln of 2a, and I will then deduct the lower limit substituted, so a plus ln a, which leads to 2a plus ln of 2a minus a minus ln a. Well, 2a minus a is simply a, and ln of 2a minus ln a, I can use the fact that I've got the difference of two logarithms. I can do the logarithm of the quotient, which leads to a plus ln of 2a over a, which is of course a plus ln 2, and we have been told that this is equal to ln 7, and therefore a is ln 7 minus ln 2, which can be further combined into a single logarithm as a being ln of 7 over 2. Well, we had that a is ln k, where k is a constant to be found, and therefore we can now conclude that k is equal to 7 over 2. In question 5, curve C is defined parametrically as x is 2t minus 1 and y is 4t minus 7 plus 3 over t, and we need to show that the Cartesian equation of this curve can be written in this form, where a and b are integers to be found. Well, I will start by taking the parametric equation for x, which says that x is 2t minus 1. I will make t the subject and substitute into the parametric equation for y to eliminate t and obtain a Cartesian equation for the curve. So we have that x plus 1 is 2t, leading to x plus 1 over 2 is equal to t, and therefore we have that y is 4t minus 7 plus 3 over t, which can be written as 4 times x plus 1 over 2 minus 7 plus 3 over x plus 1, and the over 2 comes in the numerator to avoid seeing fractions within fractions that will make the whole expression seem a lot more complicated. And now the 4 with the 2 cancel out to give me a 2 in the numerator. So I have that y is 2x plus 2 minus 7 plus 6 over x plus 1, which further simplifies into y is 2x minus 5 plus 6 over x plus 1. I will multiply throughout by x plus 1 to express everything over the denominator of x plus 1. So it's 2x minus 5 times x plus 1 plus 6 and all of it over x plus 1. I will now expand the numerator to get 2x squared plus 2x minus 5x minus 5 plus 6 over x plus 1. I will collect like terms in the numerator to get 2x squared minus 3x plus 1 over x plus 1. If I compare with the expression I was given here, we can see that the a is the -3 and the B is the 1. So my final line would be that therefore A is -3 and B is 1. Question 6 is a modeling question. We've got a company planning to extract oil from an oil field. We've got the daily volume of oil, capital V, which is measured in barrels, that we can extract depending upon the time T years after the start of drilling. And we've got two different models. We've got a linear model as shown here. We know that the initial daily volume of oil extracted was 16,000 barrels, and 4 years later this dropped to 9,000. And for part A, we are asked to use this linear model because it's a straight line model to estimate the daily volume of oil that will be extracted 3 years after the start of drilling. So for this one, I will start by finding the gradient of the straight line. We actually have 2 points through which the line passes, the 0, 16,000 and the 4, 9,000. So I'm just going to do y2 minus y1 over x2 minus x1 to get the gradient. So 9,000 minus 16,000 over 4 minus 0. This gives an answer of negative 1,750. We know that the line cuts the vertical axis at 16,000. That's the y-intercept. And therefore we have that V is 16,000 minus 1,750 t. And we need to find V when t is 3. So when t is 3, V is 16,000 minus 1,750 times 3, which gives an answer of 10,750 barrels. Don't forget to include the units here because it's a modeling question, so all the answers should be in context, and in this particular case it means stating units. In II, we are asked to write down a limitation of using model A. Well, if we look at the straight line here, we can see that at some point it's going to go negative, which means a negative volume will be extracted, which is obviously not possible. So we could simply say that after a long time, the model predicts a negative volume, which is not possible. We are then asked to use the exponential model with the information provided to find a possible equation for model B. So we still have that we pass through 0, 16,000 and 4,9,000. So an exponential model should assume a form of V is capital A e to the kt, where A and K are constants to be found. We know that when t is 0, V is 16,000. So this means that 16,000 is A e to the 0, and therefore 16,000 is the value of A. We also know that when t is 4, capital V is 9,000. So we have that 9,000 is equal to A e to the 4k. We have found A to be 16,000, leading to 9,000 is equal to 16,000 e to the 4k. Now the 3 zeros on either side can cancel out, and I obtain that 9 over 16 is e to the 4k. I will take ln of both sides, leading to ln of 9 over 16 is equal to 4k, and therefore a quarter ln of 9 over 16 is the value of k. Well, the question was asking for a possible equation for the model, so we need to provide an equation for the model. So V is 16,000 times e to the quarter ln of 9 over 16 times t. Now the phrasing of the question, the referral to a possible equation, is hinting at other forms being acceptable. So one thing you could have done is say this is V is 16,000 times e to the quarter ln of 9 over 16 and all raised to the power of t, because when you've got a power raised to a power, you multiply the indices together. Now plugging this on the calculator gives you a value of 0.866. So an equivalent form would be V is 16,000 times 0.866 to the power of t. We then have to obtain an estimate for the volume extracted 3 years later. So for I will simply do when t is 3. We have that V is 16,000 times e to the a quarter ln of 9 over 16 times 3. Plugging this on the calculator, we get 10,392 barrels. The examiner here is accepting anything which rounds to 10,400. In question 7, we've got triangle ABC and also the vector AB and BC, and we need to show that angle BAC is 105.9 degrees to 1 decimal place. So let me start by reminding us that the magnitude, the modulus, the length of the vector xi plus yj plus zk is given by Pythagoras in 3D, the square root of x squared plus y squared plus z squared. So I will start by finding the magnitude of the vectors AB and BC. So the magnitude of AB will simply be 2 squared plus 3 squared plus 1 squared, square root, which gives root 14. The magnitude of BC will be 1 squared plus negative 9 squared plus 3 squared, square root, which gives an answer of root 91. I've got the two lengths of the triangle. I will find the vector AC, which is the third side here, and then I'll find its magnitude so we can proceed with the cosine rule. So to go from A to C, I can go from A to B and then from B to C, which is simply 2, 3, 1 plus 1, negative 9, 3, which is 3, negative 6, 4. So I can find the magnitude of AC. So the magnitude of AC will be 3 squared plus negative 6 squared plus 4 squared and all square root. This gives an answer of root 61. So if I go back to my triangle, AC is root 61. We've got BC to be root 91 and AB to be root 14. We are trying to find the angle BAC, which is the angle here. So I can use the cosine rule because I've got the lengths of the three sides. So we have that root 91 squared is equal to root 61 squared plus root 14 squared minus 2 times root 61 root 14 cos of the angle BAC. This leads to 91 is 61 plus 14 minus 2 root 14 root 61 cos of BAC. I will isolate the cosine term, so 2 root 14 root 61 cos of BAC is equal to 61 plus 14 minus 91. So cos of BAC is simply going to be 61 plus 14 minus 91 over 2 root 14 root 61. I'll do shift cos and we get that BAC is 105.8877 which is 105.9 degrees to 1 dp as required. Notice that because the question was asking you to show that the angle is 105.9 degrees to 1 dp, your working should include an intermediate line where the angle BAC is given to more accuracy so that you show the rounding to the printed answer. In question 8, we've got f of x here being ln of 2x minus 5 plus 2x squared minus 30 for x being greater than 2.5. And we need to show that f of x is 0 has a root alpha in the interval from 3.5 up to 4. So we are looking for a change of sign here. I will be evaluating f of 3.5. So I will substitute x with 3.5, leading to a ln of 2 times 3.5 minus 5 plus 2 times 3.5 squared minus 30, which gives an answer of minus 4.81. I'll do the same for f of 4, and I get an answer of 3.098. And noticing that one gave me a negative result and the other gave a positive result, together with the fact that f of x is continuous, I can conclude that we've got a change of sign and f of x continues, therefore there's a root in the interval from 3.5 to 4. notice that you need to mention both the change of sign and the continuity to claim the final mark for the first part. We then have that the student takes 4 as the first approximation to alpha. We have that f of 4 is 3.099, f dash of 4, the derivative at 4 is 16.67, both given to 4SF, and we need to apply the Newton-Raphson procedure to obtain a second approximation for alpha to 3SF. Well, in the formula booklet, we've got that the Newton-Raphson process is given by this. We start with the first iteration, x1, being 4, and therefore the second iteration x2 will be 4 minus f of 4, which is 3.099, divided by f dash of 4, which is 16.67, and this gives an answer of 3.81. In part C, we are asked to show that alpha is the only root of f of x is 0. So to do that, I will start by considering that solving f of x is 0 means that we need to solve a ln of 2x minus 5 plus 2x squared minus 30 is equal to 0, which is equivalent to solving a ln of 2x minus 5 is equal to 30 minus 2x squared. So if we sketch a ln of 2x minus 5 and 30 minus 2x squared, then the number of points of intersection are the number of solutions to f of x is 0. So let me start by considering y is a ln of 2x minus 5. We know that we can never have a ln of 0. That will give me the asymptote. So the asymptote is to be found at 2x minus 5 is equal to 0, leading to x is 5 over 2. Now to find the cut on the x-axis, we need to put y is 0, which leads to 0 being ln of 2x minus 5. So e to the 0 is 2x minus 5. E to the 0 is 1. So 1 is 2x minus 5. 6 is 2x. So 3 is x. This is giving me enough information to sketch y is ln of 2x minus 5. On the other hand, I need to consider y is 30 minus 2x squared. So y is 30 minus 2x squared. I notice that 2 is a common factor, so this is 2 brackets 15 minus x squared. We know that it's a parabola, an inverted parabola, so it's like this. It's a sad face parabola. We can see that when x is 0, y is 30, and also if y is 0, then we get 15 is equal to x squared, so plus minus root 15 is equal to x. This can help us draw the parabola to see exactly what's happening. So we've got the pair of axes here. We have the asymptote at 5 over 2, and the ln of 2x minus 5 cuts the x-axis at 3. And on the other hand, we've got the parabola cutting the x-axis at minus root 15 and root 15, and the y-axis at 30. We notice that there is a single point of intersection over here, and therefore we conclude that there is only one solution to f of x is 0. In 9a, we need to prove that tan theta plus cot theta is equivalent to 2 cosec 2 theta. So this is an identity. I'll start from the left-hand side and eventually work my way towards the right-hand side. So we start with the left-hand side is tan theta plus cot theta. I will write tan as sine over cos, and similarly I will write cot as cos over sine. I will be expressing everything over a common denominator of sine theta cos theta. So in order to do that, I'll multiply the first one by sine. So that's going to give me sine squared theta and cos squared theta. So we do know that sine squared plus cos squared is 1. So this leads to 1 over sine theta cos theta. And we do know that the double angle formula for sine is 2 sine theta cos theta for sine 2 theta. So I will multiply top and bottom by 2 in order to see the denominator becoming sine 2 theta. So it's 2 over sine 2 theta, which is of course 2 cosec 2 theta, which is the right hand side as required. In B, we are asked to explain why the equation tan theta plus cot theta is 1 does not have any real solutions, and I will start by using the identity we've just proved. So if we have tan theta plus cot theta is equal to 1, using the proven identity, I can write this as 2 cosec 2 theta is equal to 1, which leads to cosec of 2 theta being a half. Well, we know that cosec is the reciprocal of sine, so this means that we can write this as sine of 2 theta is equal to 2. But we do know that sine of any angle varies between -1 and 1, so it can never be the case that there's an angle theta for which sine of 2 theta is 2, and therefore we have no real solutions. So we need a statement: since -1 less than or equal to sine 2 theta less than or equal to 1, the given equation has no real solutions. In 10, we have that theta is measured in radians, and we need to prove from first principles that the derivative of sine theta is cos theta, and in doing that, we may assume the formula for sine A plus minus B, so the compound formula for sine, as well as the fact that as h tends to 0, sine h over h goes to 1, and cos h minus 1 over h goes to 0. So let's start with something that is provided in the formula booklet, that is that f dash of x, the derivative of f of x, is the limit as h tends to 0 of f of x plus h minus f of x over h. In our case, f of x is sine x. So the first thing to do is find an expression for f of x plus h, which is of course sine of x plus h. So there it is. I'll be using my compound formula here to expand sine of x plus h. This is going to be sine of x cos h plus cos x sine h. And therefore I can proceed in finding an expression for f of x plus h minus f of x over h. So this is going to be sine x cos h plus cos x sine h minus sine x and all of it over h. I will be separating the sine x with the cos x terms, so I'm looking at the sine x cos h minus sine x over h plus cos x sine h over h, which can be further written as sine of x brackets cos h minus 1 over h plus cos x sine h over h. So we have that f dash of x is the limit as h tends to 0 of sine x cos h minus 1 over h plus cos x sine of h over h. And now it's the time to use the given information. Sine of h over h goes to 1 as h goes to 0, so this will go to 1, and the cos of h minus 1 over h will go to 0, so this goes to 0, and therefore we are simply left with cos x. So we have just shown that the derivative of sine x is cos x from first principles as required. In question 11, we've got an archer who shoots an arrow, and the height capital H meters of the arrow above ground is modeled through this formula here, where d is the horizontal distance of the arrow from the archer in meters. If you look at the formula, it's a quadratic, it's a parabola. The coefficient of d squared is negative. We can see that when d is 0, h is 1.8, so it should look something like this. And in part A, we need to find the horizontal distance traveled by the arrow as given by this model. When the arrow hits the ground, then capital H is 0 because it's exactly on the ground, which means we need to solve minus 0.002d squared plus 0.4d plus 1.8 is equal to 0. We can use the quadratic formula function on the calculator. I will show the substitution here. So d is minus b plus minus b squared minus 4a times c, all of it square root, and over 2 times a, so 2 times the negative 0.002. This gives answers of 100 plus minus 10 times root of 109. If we look at the decimal form of these solutions, it's minus 4.40 or 204. So we cannot have a negative height. which means that we conclude that the distance when we hit the ground again is 204 meters. Remember, we need to give units with our answer to claim full marks here. In part B, we are asked with reference to the model to interpret the significance of the 1.8, the constant term in the formula. Well, we do see that if we put D is 0, then we get that capital H is 1.8. So the D is the horizontal distance. So if D is 0, so the moment we fire the arrow, the height above ground is 1.8. So that must be the height from which the arrow is initially fired. In C, we are asked to put the expression for capital H in this form, so we need to complete the square. So starting with 1.8 plus 0.4d minus 0.002d squared, the first thing I will do is take out the minus 0.002, so I'm going to write this as 1.8 minus 0.002 times d squared minus 200d. So I want the coefficient of d squared to be exactly 1, so I can proceed with completing the square. So this leads to 1.8 minus 0.002, and I open brackets, it's d minus 100. Remember, it's always half the coefficient of d, so minus 200 will give me minus 100 in the bracket, minus 100 squared, and I close the curly brackets, which leads to 1.8 minus 0.002 d minus 100 squared minus 10,000. I will further expand this to give me 1.8 minus 0.002 brackets d minus 100 all squared plus 20, leading to 21.8 minus 0.002 times d minus 100 squared. And therefore we conclude that A is 21.8, B is 0.002, and C is 100. Alternatively, we could have taken the original expression 1.8 plus 0.4d minus 0.002d squared and equate it with the given expression A minus capital B d minus C all squared. I will expand the right hand side to give me A minus B brackets d squared minus 2cd plus c squared, and I will further expand this to give me A minus capital B d squared plus 2bcd minus bc squared, and I will be equating coefficients. So the coefficient of d squared on the left hand side is negative 0.002, which is equal to minus b, which is the coefficient of d squared on the right hand side. So we have that minus 0.002 is equal to negative b, and therefore b is equal to 0.002. Looking at the coefficient of d, on the left hand side we've got 0.4d, and on the right hand side we've got 2bcd. So this leads to 0.4 is equal to 2bc, and therefore 0.4 is 2 times 0.002, the value of b we just found, times c, which leads to 0.4 is equal to 0.004c, and therefore we get that 100 is equal to c. And finally, we will be looking at the constant. It's 1.8 on the left hand side, and it's a minus bc squared on the right hand side. So 1.8 is equal to a minus bc squared. So 1.8 is equal to a minus 0.002 times 100 squared. This leads to 1.8 is equal to a minus 20. So we get that 21.8 is the value of a. So we can conclude that 1.8 plus 0.4d minus 0.002d squared can be written as 21.8 minus 0.002 brackets d minus 100 all squared. It is then decided that the model should be adapted for a different archer, and the adapted formula is given here. It says find the maximum height of the arrow above ground for this new model. So I will be using my answer to the previous part. I noticed that the structure, the formula for capital H is very similar to the formula we originally had. So I will start by writing that capital H can be written as 0.3 plus 1.8 plus 0.4d minus 0.002d squared. We already have completed the square form for this part here, so I can write this as 0.3 plus 21.8 minus the 0.002 brackets d minus 100 squared. So we can see that the maximum height will be attained the moment this bracket here is 0, so when d is 100. So if d is 100, we simply get that the height will be 0.3 plus 21.8. The reason is that something squared will always give you something positive. So essentially, we are from 0.3 plus 21.8 and lower. So the maximum height, which I will call H max, is simply going to be 0.3 plus 21.8, which gives an answer of 22.1 meters. And the horizontal distance at which this will be attained will be at 100 meters. In 12, we've got a control experiment where the number of microbes, capital N, present capital T days after the start of the experiment were counted. We know that the model is of the form capital N is A, capital T to the B, for A and B being constants. And we need to show that this relationship can be expressed in this form. So I will actually start with the given relationship. Capital N is A, T to the B. I will take log base 10 of both sides. So log N is log of A, T to the B base 10. And I will split the right hand side into log A base 10 plus log of T to the B base 10. On the left hand side, we still have a log N, which leads to log of N base 10 is equal to log of A base 10 plus B log capital T base 10. If we compare this with what we are given, which is a log N base 10 is equal to C plus M log T base 10, then we can see that the log A is the C and the B is the M. So the only thing we need to do is state that C is log A base 10 and M is equal to B. We are then given the line of best fit on figure 3 for values of log N plotted against log T, and we need to use the information provided to estimate the number of microbes 3 days after the start of the experiment. So it makes sense to go on my scatter plot here and try to determine the equation of the line of best fit. We can see that we cut the vertical axis at 1.82, and I will also pick out a point through which I pass. I can see that I pass through this point over here, which has coordinates 1.2, 4.55. I will use these 2 points to find the gradient and then the equation of the line of best fit. So we have that the gradient is rise over run, so 4.55 minus 1.82 divided by 1.2 minus 0, which gives an answer of 2.275. I can see the y-intercept is 1.82. I'm cutting the vertical axis at 1.82. So the equation of the line of best fit is y is 2.275x plus 1.82. So recalling that we had log N base 10 is C plus M log T base 10, we have just established that the value of C is 1.82 and the value of M is 2.275. So we've got the equation for log N in terms of log T. We have been given to find capital N when T is 3. So when capital T is 3, we obtain that log N base 10 is 1.82 plus 2.275 log of 3 base 10. I will plug everything on the right hand side on my calculator. I get 2.905 ... leading to N being 10 to the 2.905 ... which means that N is 805 microbes to 3 significant figures. In part C, we are asked to explain why the information provided could not reliably be used to estimate when the number of microbes will exceed 1,000,000. Well, let's start by observing that for n being greater than 1,000,000, then what we have is that log of n base 10 will be greater than 6. So if we go back to our scatter plot for a moment, we see that for log n on the vertical axis, the greatest value we have seen is about 4.5, and we have not seen values in the region of 6, so we don't have data there. This means that 1,000,000 lies outside the range of observed data, and therefore any estimate would be unreliable. It's called extrapolation and should always be viewed with caution. In part D, we are asked with reference to the model to interpret the value of the constant A. Well, let's start by reminding ourselves that capital N is A capital T to the B. So we see that when capital T is equal to 1, then we get that N is A times 1 to the B. So irrespective of the value of B, capital N turns out to be A. And this simply means that A is the number of microbes 1 day after the start of the experiment. In 13, we've got a curve C defined parametrically as shown here. T varies between 0 and pi, and we need to obtain an expression for dy dx in terms of t. So I will start with x is 2 cos t to obtain dx dt. We know that the derivative of cos is negative sine, so the dx dt will be minus 2 sine t. And y is root 3 cos 2t, which takes dy dt to be minus 2 root 3 sine 2t. It's the chain rule. The derivative of 2t is 2. That's why we have the 2 here. And the derivative of cos is negative sine. So we have that dy dx, the derivative of y with respect to x, is dy dt over dx dt. So in our case, it's going to be minus 2 root 3 sine 2t over negative 2 sine t. I can stop here because I haven't been told to put my answer in a particular form. I could simplify it. Well, I'll take it up to root 3 sine 2t over sine t, and I'll stop there. That will give me full marks. If I stopped here, I will still get the full marks for part A. We are then told that there's a point P on C where t is 2 pi over 3, and the line L is the normal to C at P. And we need to show that an equation for D is normal is given by 2x minus 2 root 3y minus 1 is 0. So for this part, I will start by saying that when t is 2 pi over 3, I need to find the value of x, the value of y, and the value of dy dx. So x is 2 cos of 2 pi over 3. I'm substituting t into the parametric for x. This gives an answer of negative 1. Y will be root 3 cos of 2 times 2 pi over 3. So this is giving an answer of minus root 3 over 2. And dy dx, I will substitute t is 2 pi over 3 into the expression we obtained in part A. It's root 3 sine of 2 times 2 pi over 3 divided by sine of 2 pi over 3. This gives an answer of minus root 3. Now for the gradient of the normal, I will simply flip and change the sign of the dy dx. So this will be 1 over root 3. And then we've got a point, we've got the gradient. I'll be using y minus y1 is m brackets x minus x1 to obtain the equation of the normal. So we've got that y minus negative root 3 over 2 is equal to 1 over root 3 brackets x minus negative 1. So this leads to y plus root 3 over 2 is equal to 1 over root 3 brackets x plus 1. I will cross multiply by root 3 to get root 3y plus 3 over 2 is equal to x plus 1. I will then multiply throughout by 2 to get rid of the denominator. So 2 root 3y plus 3 is equal to 2x plus 2, which means that if I collect everything on the right hand side, I get 0 is 2x minus 2 root 3y minus 1 as required. We are then told that the line L, the normal, intersects the curve C again at the point Q, and we need to find the exact coordinates of Q showing clearly are working. So at the moment we've got the parametric equations that describe a curve C. X is 2 cos t and y is root 3 cos of 2t. And we also have that 2x minus 2 root 3y minus 1 is 0 is the equation of the normal. So I need to solve this simultaneously, and it makes sense to substitute the parametrics into the equation of the normal to get an equation in t. So this leads to 2 times 2 cos t minus 2 root 3 times root 3 cos 2t minus 1 is 0. So we have that 4 cos t minus 6 cos 2t minus 1 is 0. We know the double angle for cos 2t, so I'm going to use that to get a quadratic in cos t. So minus 6 times 2 cos squared t minus 1 close brackets minus 1 is 0, leading to 4 cos t minus 12 cos squared t plus 6 minus 1 is 0. I will collect everything on the right hand side. Leading to 0 is 12 cos squared t minus 4 cos t minus 5, a quadratic in cos t, which factorizes into 6 cos t minus 5, the first bracket, and 2 cos t plus 1, the second bracket. So we either have that 6 cos t minus 5 is 0, or 2 cos t plus 1 is 0. So this means that 6 cos t is 5, so cos t is 5 over 6, or 2 cos t is negative 1, so cos t is minus a half. Now for cos t being 5 over 6, I don't really need to go and find the value of t. We're looking for the coordinates x and y, and we do know that x was 2 cos t. So if x is 2 cos t, I will substitute cos t with 5 over 6, and this gives an answer of 5 over 3. And similarly, y was root 3 cos 2t, which is root 3 times 2 cos squared t minus 1. So this is root 3 brackets 2 times 5 over 6 squared minus 1. So this gives an answer of 7 root 3 over 18. And for the cos t is minus a half, I could put x to be 2 cos t, so 2 times minus a half, which gives an answer of negative 1. Recall that negative 1 was the value we obtained for x when we were looking for the point P, which means that for cos t being minus a half, this is the point P. So the point Q here has coordinates 5 over 6, 7 root 3 over 18. In question 14, we've got a sketch of part of the curve C with this equation here. We are being given a table of values for x and y for x between 1 and 3, and we need to use the trapezium rule with all the values of y to obtain an estimate for the area of S, giving our answer to 3 decimal places. So we know that the trapezium rule is used to find an estimate for the area. So the area S will be approximately a half times the height of the trapezia, which is simply the difference between two consecutive values of x. So that's going to be 0.5 in this case. So a half times 0.5, and then it's the first and last y values once, so 3 plus 2.2958 plus twice all intermediate values, so 2 times 2.3041 plus 1.9242 plus 1.9089. Plug everything on the calculator, we get 4.39255. We have been asked to give our answer to 3 decimal places, so my final answer will be 4.39323 dps. In part B, we are asked to explain how the trapezium rule could be used to obtain a more accurate estimate for the area of S. Well, if I use more trapezia, I'll be able to follow more closely the curve, and therefore this will lead to a more accurate estimate. So the answer to part B will be use more trapezia or increase the number of strips. In part C, we are asked to show that the exact area of S can be written in this form: A over B plus ln C, with A, B, and C being integers to be found. So we know that to find the area S, we will be using analytic integration. So we will be integrating from 1 up to 3, x squared ln x over 3 minus 2x plus 5 dx. The problem is obviously the x squared ln x over 3, and I'll be using integration by parts for that one. So the integral of x squared ln x over 3 dx, we need to choose our u and our v dash. I'll put u to be ln x because I know how to differentiate it. It gives me 1 over x. And I will put v dash to be x squared over 3, which means that if I integrate v dash, it will give me v to be x cubed over 9. And therefore we have that the integral of x squared ln x over 3 is uv minus the integral of u dash v. So this will be x squared ln x over 3 minus the integral of 1 over x times x cubed over 9 dx, which takes me to x squared ln x over 3 minus the integral of x squared over 9 dx. So this is x squared ln x over 3 minus x cubed over 27. I don't put the plus c because I've got limits in the original integral here, and therefore we have that s, the integral shown here, is going to be the answer we just found: x squared ln x over 3 minus x cubed over 27. We've got the integral of 2x, which is 2x squared over 2. We've got the integral of 5, which is 5x, and the limits are 1 and 3. We notice that the 2 with the 2 will cancel out, and therefore I will substitute the upper limit of 3 to give me 3 squared ln 3 over 3 minus 3 cubed over 27 minus 3 squared plus 5 times 3. This is the upper limit substituted, minus the lower limit of 1 squared ln of 1 over 3 minus 1 cubed over 27 minus 1 squared plus 5 times 1. So we need to show the work clearly. We have 3 ln 3 minus 1 minus 9 plus 15. That's the first bracket, minus 0 minus 1 over 27 minus 1 plus 5. This leads to 3 ln 3. All of the constants, plug them on the calculator, you get 28 over 27. The only thing missing is to match the exact form shown in the question. So I will write 3 ln 3 as ln of 3 to the power of 3 plus 28 over 27, which gives an answer of ln 27 plus 28 over 27. In 15, we're being given a sketch of the curve with equation y is f of x, where f of x is here, and we need to show that the x-coordinates of P and Q, the maximum and the minimum turning points respectively, are solutions of tan 2x is root 2. So starting from the fact that the 2 points are turning points, we know that at point P and point Q, we should be having f dash of x to be 0, and therefore we need to obtain an expression for the derivative of f. So f dash of x, we are looking at the quotient here, so we'll be doing the quotient rule. I differentiate the top to get 4 brackets 2 cos 2x, and I keep the bottom of e to the root 2x minus 1, minus keep the top, and I differentiate the bottom to give me root 2e to the root 2x minus 1, and all of it over the bottom squared, which is e to the root 2x minus 1 all squared. Now we notice that in the numerator there's a common factor of 4e to the root 2x minus 1, which leaves us with 2 cos 2x minus root 2 sine 2x, all of it over e to the root 2x minus 1 all squared. Now, for f dash of x to be 0, it must be the case that either the e to the root 2x minus 1 is 0 or the bracket is 0. Well, e to any power can never give you a result of 0. So we conclude that we must be having 2 cos 2x minus root 2 sine 2x is equal to 0, which leads to 2 cos 2x is equal to root 2 sine 2x. Remember, we're trying to arrive at tan 2x is root 2, so what I will do, I will divide both sides by root 2 cos 2x, because this will give me the tan 2x on the right hand side. So the cos 2x with the cos 2x cancel out, 2 over root 2 is root 2, and on the right hand side the root 2 cancels out, and sine over cos is tan, so we get that tan 2x is root 2 as required. In part B, we are asked to use our answer to part A to find the x-coordinate of the minimum turning point on the curve with the equation y is f of 2x and y is 3 minus 2f of x. So let me start by solving tan 2x is equal to root 2. My principal value is shift tan of root 2, which gives an answer of 0.9553 ... So 2x is my principal value plus pi k. And I will divide throughout by 2 to get that x is 0.47765 ... plus pi k over 2. Setting k to be 0 will give me the first solution to be 0.478, and setting k to be 1 will give me the 2.048. If we go back for a moment to our graph here, we see that the point P must be having an x-coordinate of 0.478, and it's the maximum point, and point Q is having an x-coordinate of 2.048. So this means that the 0.478 here, this is the maximum. Let me make a note of this. And similarly, the 2.048 is the minimum. Now the first part says y is f of 2x, so we're looking at the transformation affecting the x values. We divide x by 2. This is a stretch along the x direction, scale factor over half, which means that if we are looking for the minimum turning point, the x-coordinate of the minimum turning point, I'm just going to take the x-coordinate of the minimum here and divide by 2. So that means that we have that x should be 2.048 divided by 2, which gives an answer of 1.024. In II, things are a bit more complicated. We've got y is 3 minus 2f of x. So two transformations here affecting the y's. So first of all, the negative 2 here means we multiply y by negative 2. And then the 3 means we add 3 to y. So multiply y by negative 2, then add 3 to y. We need to think of how the graph is affected. Now, the fact that we are multiplying by negative to the y's means that the positive y's become negative and vice versa. So this is equivalent to a reflection along the x-axis. So let me make a note of this. We are looking at a reflection along the x-axis. The x values are not affected. So if I briefly go back to my graph here, it's gonna look something like this. And we see now that the minimum became a maximum and the maximum became a minimum. Well, in part B here, we're looking for the x-coordinate of the minimum turning point. So for the minimum turning point, I'm just going to take the x-coordinate of the maximum in the original, and that's going to be my answer. So essentially, what we have to realize is that the reflection along the x-axis is making maxima and minima interchange. So let me make a note of this as well. Final answer for II is that x is 0.478.